Okay, let's get started. So Tuesday, uh, we started talking about stack-based buffer overflow. We briefly discussed the history of it. We talked about the information a save function needs to run, discussed several calling conventions on 32-bit and 64-bit. We also had several examples. We show how to override local variables. So how is everyone doing with homework 2 so far? Okay.
Confused on number 3.
Okay.
Yeah,
Okay, we can talk after this class.
that would be fabulous.
Yeah, probably we can go to the tent there because I don't have a office on campus, so maybe just go to the tent. Or if you guys want to discuss with me anytime, just ping me on Slack. We can schedule a Zoom session whenever you guys need. Okay, so this class, we will talk about override the return addresses so we can execute a function. If we have time, we can also discuss how we can override multiple return addresses, and then we can chain several functions together, and also we can call or return to a function with parameters. So next week, we will talk about how to inject your own share code into the address space. So your own share code is just arbitrary code. So with that, you can do anything on the computer. Okay, so what we are doing here is called control flow hijacking, because the return address from C code point of view is just a pointer, right? It's an address. In C, an address is a pointer. It points to what? It points to code, okay? And that piece of code will be executed at some point. And if you override that return address, you are basically hijacking the control flow. It's supposed to execute back to the function which called the core E. However, now you are going to anywhere, right? You hijack the control flow. So several registers are very important here. Obviously, the saved EIP or saved RIP is extremely important. And that is the return address on the stack, right? So basically, before the call instruction, you already have that address in the EIP register, but the call instruction will push that address onto the stack, then set a new value to that EIP or RIP, right? Also, we have the frame pointer, the EBP or RBP on the stack, the saved one, and the EBP and RBP register will point to the saved one there, right? So that is our baseline, base pointer. When we execute in that function, we use that to reference local variables. We use that to reference parameters, right? So this Tuesday, you already saw that right now, for the code we are looking at, there is actually no mechanism to prevent a dangerous function like string copy to overwrite those values. They can be overwritten. So in this class, we will say how we can exploit that vulnerability. Not just to crash the program. Instead, we want to eventually achieve arbitrary code execution or just to give us the flag, right? So the ultimate goal of today is to overwrite the saved return address on the stack. I think next week or maybe the week after, we're going to overwrite the saved EBP on the stack or RBP value on the stack. So the goal here is to change that value so it points to attacker-controlled code. Sometimes also data. Here, more like a code. Then when the program, that function exits or returns, then the program will continue execution at the attacker's code, right? So this is one of the most common vulnerabilities in C, C++ programs. So here is our slightly modified example code from Overflow local 1. So this one is called overflow return one. We have a main function. The main function takes two arguments, but we're not really using it. At the beginning of the main function, we print out the address of print flag. Okay, you can consider this is a library function. A library function I already put there. As long as you call this function or execute this function, it will print out the flag for you. Okay, so this week you still have the luxury of this function. Okay, next week we will not have this function anymore. Because obviously when you hack real world production software, they are not going to have convenient functions like that for you. Right? So print out the address for you. Then we call the vulnerable function, vol_foo. After that, there will be IPT the foo print out. So the vol_foo, a very simple program, a local buffer, 6 bytes in C code. I keep saying that 6 bytes in C code because the compiler may give it more bytes. And we're asking for 6 bytes. Then there is a gets function. So now we're not using string copy, but gets. Gets will get input from standard in, right? So in this case, for this terminal program, the standard in is just the terminal, the type from terminal. Okay. So previously, the input was from command line argument. Then the program just returns. This function just returns. When this function returns, it will call IPT the foo, right? So if you just input 6 bytes, then nothing will go wrong. The vol_foo will return, print IPT the foo, then the program will exit. So a little bit more about the gets function. So this is a standard C library function. So whenever you hack, you say a function you are not familiar with, make sure you read the document. You can just Google online or use man command, get the document. So of course, you already kind of understand what it does. But usually, some functions are slightly different. For example, this one will read a line from std. Okay, it will not read 2 lines. Okay, only 1 line. So it means if there's OA, it will stop. So it will stop at a terminating new line or end of file, and then replace it with 0. Okay, so there is no check for a buffer overrun. And because of that, it is possible we have this buffer overflow. So when you program, no, you should not use functions like this. But some legacy programs, C programs, system may still have dangerous functions like this. Or even if some new programs are not using dangerous functions like this, they are vulnerable in other ways. There's still memory vulnerability. So next, we are going to look at this 9 by 9 to say how we can override this. After Tuesday, I assume you already have a basic idea here. So we call vol_foo from main function, right? So at the very beginning of vol_foo, the very first instruction, the ESP should point to the return address on the stack, right? And this return address is somewhere in the main function, actually after the function call to vol_foo. So ESP points to here. The first instruction here is actually end BR32. This function doesn't really matter for now. Okay. That's actually a CPU feature to stop some kind of control flow to do control flow integrity. Right now, we're not really using it. So this instruction was introduced maybe several years ago, which means older CPUs don't really have this instruction. So when Intel or ARM, they introduce a new instruction, the new instruction actually fall into the category of undefined or ignored instructions for the previous instruction set. So if an older CPU says an instruction like that, it doesn't support instruction, it will just treat this as a no operation, doesn't do anything. But a new CPU may trigger some new security features. For now, we just ignore. The real first instruction here is push EBP. What happens is now we will have saved EBP on the stack. And this saved EBP actually points to somewhere higher, which is the main function's stack frame. After that, just the standard move ESP to EBP. So both of them points to the saved EBP. After that, we subtract 18 in hex bytes. After that, we subtract another 3 bytes. So here it looks a little bit weird, right? Why the compiler is doing this? Why the compiler didn't just merge those two? Okay. So that's probably because the optimization levels I was using. I think for most of those programs, I just compare them with 0, so no optimization. So if the compiler is smarter, the compiler can merge those. Okay. So anyway, now we have 24 bytes here, 12 bytes here. From here to here is like 36 bytes. Now we know effective address from EBP minus E. E is 14 bytes. Okay. So now we know that we're getting the address of 14 bytes from the beginning to the saved EBP. We don't know what that is yet. It's actually the address moved to EAX. The EAX was pushed onto the stack again. So the reason we are pushing this one is because we are making another function call, which is gets. Okay, and gets only takes one argument, which is the buffer, right? So now you can say the buffer's address, the buffer is actually at EBP minus E. Okay, so we asked for how many bytes in the C code? 6 bytes. But in this case, the compiler actually are giving us 14 bytes. Right? The compiler gave us 14 bytes. Then we make the function call to gets. That's a C library function. We do not really get into it. So it will keep moving, pushing things onto the stack. It may call a lot of other functions. The stack may go down. But eventually, when that gets returns, when the functions gets calls returns, the ESP should point to here. So that's the stack balance. That's the core's job to make sure the stack is balanced. So when gets returns, ESP should point to here, just like before it is called. Now after that, ESP was at 16 bytes there. Then this function will just return 0. So we move 0 to EAX. When we move 0 to EAX, we are setting the return value. Okay. Now we have the leave instruction. The leave instruction is equivalent to move EBP to ESP, then pump EBP. So the first thing we do is actually move EBP to ESP. Before that, ESP was pointed to here. Now we move EBP to ESP, so both of them points to here. So you can see that this instruction here, for this particular function, doesn't really matter. Okay. The compiler didn't optimize it away. It can. Maybe a 0, 02 version may optimize this away, but it doesn't do anything, technically. So after that, we pop EBP. After we pop EBP, EBP will point to a much higher address, which is the main function's stack frame. And because we have a pop, ESP now points to the return. This is the saved E. Okay. So the value here, okay, none of them was clear. Okay, actually they're not clear, but now technically they are undefined values, but they're still there. So there may be some information leakage problem as well. Now after that, we have the return instruction, and this return instruction will pop this return address into EIP and ESP moves out. So the vulnerability here is very, I think it's straightforward. Now, we can start overwriting or writing and the address EBP minus E, okay? Because that's where buffer is, right? That's where we're going to put data. After we put data, let's say that's 14 bytes. After that 14 bytes, there will be a saved EBP address, right? 4 bytes. But what we're trying to overwrite is this return address here. We want to overwrite this address to the address of print secret. That's what we want to do. The reason we do that is the return address will change to print secret. So when this function, this piece of function returns, it's not going to return to the main function, okay? It's going to return to the beginning of print secret. So we are gonna execute the print secret function, which gives us the flag. Does that make sense? Okay. So to override that, how many bytes we need? We need 14 bytes of garbage, right? Because the buffer is 14 bytes, not 6 bytes in the C code. Then we have the saved EBP, which is 4 bytes. We do not care about this value, okay? Whatever is there, doesn't really matter for us. Because we put garbage here, eventually we will get a segment 4, but doesn't matter. Okay? Because what we are doing here is this value used to be the string pointer of the main function. Now we overwrite this return address. We're not returning to the main function. So this value actually becomes the frame pointer for print secret, right? Because we're calling print secret. So, but it doesn't really matter because we're not using any important data there. But when print secret eventually returns, it's going to dereference from here or somewhere near this, and that will trigger a segment fault. But before that, we already get what we want, which is the flag, right? So that's why at this point, we don't care about this value. What we care about is this value. So the exploit actually is very simple. Looks like this. We use Python 2, like I said, because the syntax is easier. We print a garbage character for 18 bytes. Now you get why we have 18 bytes, right? 14 bytes of buffer and 4 bytes of saved EBP. Okay, that's 18 bytes of garbage, whatever you put here. Then after that, you need 4 bytes of the address of the print secret function. And you pipe this whole thing, that will be like putting in 2 bytes, putting in 3 bytes, maybe with a ending 0 will be 23 bytes. That will be piped into the program. We use a pipe here. So now we're not using a $ Python, that's one for command line. So we type this into this. So after we do this, we should be able to get the flag. So let's go to program. So we're going to debug this so you can say step by step how it works. But before that, let's just run this program. When we run this program, very conveniently, the program already print out the print flag function address for you. Okay. Obviously, in the future, other programs will not do this for you. You need to figure out where they are. So this program doesn't really take input from command line arguments. So if you do here, don't take it. Okay, doesn't matter. So now what we can do is we're going to pipe something into this. Let's say if we just put 14 bytes of A there, what will happen? Nothing. Yeah, it will just print out. Actually, it may overwrite because at the end we're going to add a 0, right? And that 0 will override part of saved EBP. So we may get a segmentation fault. But if we do 13 bytes, it should be nothing, just the print out IP to the full, right? So 13 bytes, yes. 14 bytes, we may get a segment fault there, actually. Yes, we do get a segment fault here for this is because this is because we overwrote 1 byte of this saved EBP, right? So the valve returns. Yes. So the valve can successfully return to the main function. Then the main function eventually will return. But when main function returns, its frame pointer was changed. And it cannot successfully return. Yes. And because of that, we get a segment fault. So if we overwrite 17 bytes, which is actually overwrite 18 bytes, then we will fully overwrite the saved EBP part. So do we still get the IP to the full print out? Yes, we do. Yeah. So because function valve, the same as the previous one, function valve can successfully return. So it will return here. So we will get IP to the full, but after that, main function cannot successfully return. Okay. So if we do this, we still get the address of print flag, IP to the full, the segmentation fault. So if we do 1 more bytes, we do 18 bytes. So 18 bytes, what will happen? We're going to fully overwrite the saved EBP and also overwrite 1 byte of the return address. Okay. We're overwriting that to 0. But if it is already 0, then nothing will happen. If it's not 0, then what will happen? So what kind of output we should get here?
Segmentation fault. Or the address is
Get the address, okay?
segmentation fault.
Yes, so we are not going to get an IP to the full because valve cannot successfully return unless that byte is already 0. I guess it's not the case. Okay, it's not that case. So this is the main function. Then we call into valve. Valve didn't return to the address we're supposed to return to. Now we have 18 bytes. We can actually return. So after that 18 bytes, we can put the return address. We can overwrite to wherever we want, right? So let's say we want to overwrite to where print flag is.
What is the significance of the /x's?
That means it's hex value.
Oh.
Yeah, we're giving to a hex value. Yeah. Let's say if you
would explain why the dynamics of that.
yes, if you do not do /x, you do 6D.
Yes.
This will be a string. This will be string. The 6 here will be what? Will be ASCII value 6, will be like maybe 36 or 66, whatever. Yeah.
Okay. Okay.
Yeah.
I've been.
Yeah.
I was just trying to get it to do 2 by 2 on problem 3. Yeah.
Yeah. That's probably the problem. Yeah.
Okay. Okay.
So this is part of the Python syntax. Yeah.
Yep.
So 6.2, 5.5, 5.6. Okay. So that is where that program is, right? Let's say if the order is correct. This is higher address. Yeah. So 60. Okay. So if we do this, what should we get? Yes, we should get first is this string, right? Then we're going to get the flag. Are we getting IP to the full? No, because we're not returning to the main function. But after we're getting the flag, here we're returning to the function print flag. So this function eventually it will also return, right? So it cannot return successfully because we don't have a setup frame pointer for it. We put a garbage there. Remember, we put it just for A there. So after that, we're still eventually we're getting a segmentation fault, right? So that's what we get. We get a flag, and we get a segmentation. Oh, by the way, the flag I give you guys, the flag is randomly generated, at least for every one of you. Yeah, go ahead.
So instead of reading by 14 and then we somehow figured out the names under the 14 and the things at the time print flags are going to get ICD.
You can. It's more complicated. Yeah, and besides fun, I do not see any reason you want to do that, right? I mean, you're not really getting much, yeah, but it's possible, yeah.
So base pointer will, if we don't override the base pointer, will return back to me.
Yes, so you do not override that, then you are technically you will return to whoever the function called the main function, the instruction after the name, because eventually you are going to use that return address. Actually, it's a little bit more complicated than that. There will be 4 bytes off. We actually will talk about that later, maybe not today. There will be 4 bytes off. Yeah, because when you in a code, let's say libc start main function, that function is a C library function. That function actually calls the main function, right? Here, we are directly returning to the print flag. Nowhere actually called it. So the stack will look a little bit different. There is a slight difference there. There will be 4 bytes off in this case. Yeah. But we're going to utilize this for something. Especially when we chain things together, we're going to utilize that. It makes some of the attacks actually more convenient. Anyway, so let's take a look at the this function. Where is print flag? This is print flag. You can see this address here. This is not a runtime address. This is actually an offset. So the offset we have is 1260. The runtime address we got was 62. Yeah, here. The last 2 bytes is 6260, right? So this is the offset of that in the file. There is a base address added on top of that offset. Okay. So if we look at this print flag function, okay. So when we return to, we actually return to here, right? We return to there. Is there any other place we can return to instead of this one and still get the flag? So this is 60. What if we return to 6E? What will happen? 60 is here. That's an NBR32 instruction. If we return to 6E, we're actually returning to here, right? So right now, we don't know what instruction that is. It may be this whole set may be a new instruction, and that's very likely to trigger a segmentation fault or whatever, right? But if we return to 71, what will happen? So basically, we skip the NBR32 instruction, right? That should also give us a flag because I already told you this instruction right now is not doing anything, right? So let's try that. So if we return to 6E, very likely we're getting a segmentation fault. Oh, we're actually getting a flag for this one. Go to 6E, F. So this is interesting. When we do 6E, so when we return to here, maybe this part is interpreted as a valid instruction, but doesn't do much. So we still keep running and we get the flag. Right? We actually 6E here, we get the flag. But if we return to this place, and this will not be a valid instruction. So we're doing 6F, right? It's not a valid instruction. What? I don't know what this part is interpreted as. We can Google that. Let's say x86 disassembler online. So we want to put the hex value there. What's the value? So when we do this part, those 3 bytes. What? Okay. This. Oh, I think it's Northeastern firewall. Doesn't allow us to access this website. Yes, some of the firewall works like that way. The first time you connect to it, it's checking what is there, then find something suspicious, then they do not allow you to do that. Let's see if I can find another tool. Otherwise, we just debug this part. This looks like this website works. Sounds wrong.
So this is not assembly.
Oh, I should do this, right? Oh, okay. Let's just debug this. Debug will be easier. So we just do a GDB. The debug this program. The debug this program, we set a. Don't need to set a breakpoint. Doesn't matter. We run this program. We want to disassemble print flag function. Then this is the code we are getting, but we want to interpret from 6E what code it is, right? So we use exam. Then we want to interpret just one instruction. So one I means instruction. From here, from the address of so if you want to put address there, you need to use a $sign. So if we put 60 there, it should give us the N32. Oh, I should not put star like this. It give us the N32. Star means dereference. So if we put E there, what give us? Oh, it actually give us a log. That's why we were lucky there. It actually give us a that is 3 bytes. Actually, is a mop instruction, no operation. That's why we were lucky there. Yeah, make sense? Okay, so go back here. So if we do F, we get a segmentation fault. Then after that, we can go 70. It also give us 74. But if we do 71, then we just skip the whole first instruction, which is 4 bytes. And this should also give us the flag, right? But we're not executing. So you can say here, the instructions, the Intel architecture, the instructions, they have different lengths. Some of them are 2 bytes, some of them 1 byte, some of them could be 7, 8 bytes. And the CPU, no matter what address you gave to the CPU will interpret that from that address, which means we can actually jump into a middle of an instruction that the compiler emitted. And the CPU will say another instruction, which was not really emitted by the compiler. Actually, we're going to utilize that in return-oriented programming. So basically, huge space of code or even garbage, we will be able to find useful instructions. And we're going to chain those instructions together to do something malicious. That will be second half of the class. Go ahead.
Why does the 6770 did not give us no operand? The 6770
So that one, why we're not getting the flag?
getting the no
We don't know if it's a low. I don't think it's a low, no. But we can say that. Wait here.
he got the no, then he will get the plan.
Yeah, if it's a mob, we should return a flag. Obviously, that's just a
That's some hybrid.
that's an instruction that we don't know. Let's take a look. What's the address again? I copy that. You want to do 670, right? You want to do 70. Okay. Okay. This is actually a very special instruction. STI. It's set interrupt. Okay. So it's enable interrupt. So this may be a privileged instruction.
For 6F will get some other thing.
What?
6F again.
6F is a LOP instruction.
So we should get the flag in 6F, right?
So we were doing 6F or 6E?
50 got no.
6E we got a LOP. 6F. 6F, we are getting an instruction, okay? This is a valid instruction. This instruction this one is push this. Would this be dangerous? So for this one, did we get a flag? We didn't get a flag, right? So this one maybe, I'm not sure how this one triggers segment fault. But what we can tell is eventually this one did trigger segment fault. So that's why we're not getting a flag. Okay, so now you saw how we can return to a function. Bro. The 64-bit version of this is actually similar. This is it's assembly of the 64-bit version. At the beginning, we still have the CFI feature, which we can ignore. When we push, move, ESP to EVP, subtract, load the effective address. What interesting is here? What's the size of buffer? So this is a call to get. This is a library function. Its first argument is not on stack, right? First argument is in the register RDI, okay? So how did we get the value in RDI? We move RAX to RDI, and RAX is EBP -6. So the 64-bit version of this, the buffer size is actually 6 bytes. The previous one was 14 bytes, okay? That's why when we want to override this, we will first need 6 bytes of buffer. Then we need the saved RBP, right? How big is RBP? 8 bytes. So we still need 14 bytes of garbage, but not for the same reason of the previous 14 bytes, okay? So when you hack, you need to check the binary code, the disassembly to verify the size, okay? After that, we're going to have the return address, which is print flag, and that is 8 bytes, right? Not 4 bytes anymore. So let's try this one. Return this one. We'll solve it. You did. Okay. So if we run this program, it's going to give us the address. So this address looks like 1, 2, 3. Okay, 3 bytes. That's because I didn't print out the leading 5 bytes. It's actually 8 bytes in total. So what do we do? We do a Python 2, 3, 3. So we need 14 bytes of garbage. Then we need 8 bytes. If we do not have 8 bytes, we just put those 4 bytes there. Obviously, it's not correct. Right? So if we just put this there, what will happen?
You will fail to overwrite the lowest byte there,
Yeah.
which will cause us to type all bytes down into some random other place.
Yes, but I'm thinking it may work actually, because we're overwriting the return address, right?
Mhm.
So the higher 5 bytes may already be 0. So it may work. Yeah, that's right. It may work. There's a syntax error somewhere. Okay, I forgot about the type. Yeah, it actually works because we're returning to main, and main already have those 5 bytes 0.
Yeah.
Yeah. So actually, this
Yeah.
works. So, but if we put another byte here, that should give us a segmentation fault, right? Yeah. So we will not get a flag. But if we put 5 bytes of 0 there, it should work. So in this case, you can say we can put 5 0 there. It will be equivalent to this. But our share code, not our exploit, will be shorter this way. Okay. So if this is a remote attack, sometimes you have to utilize those kind of heuristics or whatever, because there may be other restrictions. The network side, you can only send 5 bytes, cannot send 8 bytes, right? So those kind of restrictions may exist. So this is for. Okay, then let's do something a little bit more interesting. Now we want to return to a function. Now we want to return to a function, and this function has a parameter, has an argument. So the main function doesn't give you the address of print underscore flag directly. Instead, it gives you another function's address, print secret. Right? The print secret function has an argument I, and it will check if the argument is 1, 2, 3, 4, 5, 6. If it is, it will print flag. Otherwise, it print IP the full. Also, another thing interesting is at the end of this print secret function, this function doesn't return. Okay. So this vol function returns. This main function also returns. So it's not explicit here, but implicitly it's just a return 0. If you say you do not write return 0, it's not return 0. This one explicitly says return 0. This one is different. Technically, there may be a return after this exit 0. Okay, there is instruction, but that instruction is never executed because this exit 0 is a C library function that makes a system call to the OS to kill the process. So this function never had a chance. This function never had a chance to return. Okay. This function doesn't return to. Oh, no one is calling this function here. See, no one is calling this function. Okay. Because this function never returns, it will not trigger the segment fault. It will gracefully exit. Okay. But if you call into here, it works. So use the techniques we just learned. How do we get a flag? We can overwrite the return address on the lawful stack points to this place, right? It directly points to this place, or we find out where print flag is and return to that place. Okay. But that's not the point of this challenge. This challenge, you have to return to the beginning of print secret, because I want you to do that. I want you to set up the parameter for that function. But we can't, if you only want to get a flag, obviously we can't do that. Say, well, let's try that first. We go to return true. So first, this program doesn't directly give us the address of print flag. But how do we get that address? We can still get it. We can GDB, we can debug it, or we can use other tools like NM. We can find the address there. So this is all the offset, but let's see where it is. So print flag is still 1260, and print secret is 1338. I say that, right? But the runtime address of print secret is 6338, which means the runtime address of print flag very likely to be 626, right? So we want to have this somebody here. We need to disassemble this to figure out the buffer size. So we do a object down. So let's say Overflow is here. It's actually the same as the previous one. So the buffer is at 14. Oh yeah, 14. No, we need 18. Okay. So this one, technically, we can do similar to what we did before. We do a Python 2. We put 18 bytes of garbage there. Then we put the address of print flag there, which is 60 625556. Thank you for that. Okay. So when we do this, we can still get a flag. Okay, almost the exact same exploit. Okay. But this is not how I want you to do it. I want you to return to the beginning of print secret instead of returning to the print flag. Right? So now let's see how can we do that. This is a little bit tricky actually. So this actually answers your question. This is very related to that. So what we have here is, let's say we have already override the buffer, whatever. And we're about to return from Overflow. When we're about to return from Overflow, the EBP register will point to save the EBP. Right? On top of that, 4 bytes, we have the return address. Now, we previously, what we override is this part, we just put garbage there. Let's say 4 bytes, 8, whatever. Then we put the address of print secret there, right? Now, what will happen? What happens is EBP will move to ESP, okay, the epilogue. Then EBP will get popped, right? So EBP will have our garbage value for A's there. Okay, that's garbage value we put whatever garbage value there. So after that, we are going to return. So what a return does is it's not going to change the value of EBP. So EBP stays as 4A's, but the EIP will change. Now we have the address of print secret there. And the ESP, because it's a return is also a pop, right? The ESP will move up to this place. Then we will be at the beginning of the print secret function. The very first instruction of the print secret function is push EBP. And our EBP has our garbage value for A's. So it will actually, so ESP right now points to here. Now we're going to push EBP. we're going to override this address. Previously, we used buffer overflow to override the address, but now the beginning of print secret will override this, and it will write the garbage value for A's there. After this, we will actually have two copies of those 4 bytes of 4 A's in this place. Okay. And that's what I'm talking about, the 4 bytes off, right? And after that, we're going to move ESP to EVP. So both of them point to the higher 4 bytes of those 4 A's. And now we finish setting up the stack frame of this print secret function, right? So the print secret function, EVP, will point to this address. So this is what exactly what you asked. What is different here? So when you return to the main function from Overflow, if you successfully return from Overflow to the main function, there is no buffer overflow. The main function's EVP should point to no, it will point to somewhere much higher. Okay. Not this place. Yeah. And this is also not the same place where EVP points to involve. The EVP involve points to this address, remember? Yeah. The EVP, the involve's return address is at this place. And because the print secret was never called, it was actually returned to, the EVP of print secret will be 4 bytes higher than the Overflow's EVP points to. Then this is basically the stack frame for the print secret function right now. And what does this stack frame look like? The EVP points to the saved EVP, which we put there, it's garbage, right? It's still garbage. The EVP plus 4, it's a return address.
There should be no return address, right? Because it was never called.
What?
There should be no return address for.
We can override it.
But why is it there in the first place? Because
It's not there yet. We can't override that. So we can override involve, we can override the whole thing. So the previous example, we didn't override that. In the previous example, we only override those 3 addresses, right? We didn't override beyond that. But before we didn't know what are they. Now we know that this 4 bytes will be the return address for the function you return to, okay? Then what is the 4 bytes higher than that? What?
Argument.
Yeah, the argument for that function, right? So there's the overwriting you are doing is one shot. You only got one chance to do that. Okay? But you can't overwrite that. So the parameter I will actually add this address, then the return for this function, print secret. The parameters here, return address is here. This value, you will treat it as the saved EVP. The value doesn't matter. This value doesn't matter anymore, right? So, okay, yeah.
Still kind of confused why we have 2 A's.
Yes. The reason we have 2 copies of those is because of here, right? Let's say this is the last instruction of Overflow, which is a return. And at this point, ESP should point to the address of print secret, which will overwrite there. So after return, ESP moves up, right? The EVP actually has this address, has this value, garbage for A's. Now, what is the next instruction to execute? The next instruction to execute is the first instruction of print secret, right? Then the print secret will do something like this. It will push EBP, then move ESP to EBP. Right? So if you actually return to where you're supposed to return, middle of main function, it will never do something like this. It's not supposed to, right? It should keep the stack balanced. But now the stack is not balanced. Yeah, go ahead.
I'm saying the return address is always is if you have the call machine instruction, right? In assembly, if you have call some function, then only the return address will be placed on the stack.
Yes.
But in this case, this function was never called.
Yes.
Was returned.
So with
My question is, why do we have a RET? Or maybe if you go to the next slide.
so the RET there, the address there is not created or pushed by a call instruction. It is placed there by the overwriting you are doing. So here you can consider that just the 4 bytes, right? Just 4 bytes of data. So whether it's an address or not depends on how the CPU interprets it.
So basically, points here of the print secret. So when print secret eventually returns, it will use this.
Exactly, because at the end of the print secret, there's a return instruction. And when it executes that return instruction, ESP points to that. Then CPU will think this is a return address. It's not because the call placed it there in the first place.
How it got there.
Yes.
We are writing it like.
Yeah.
So it can be garbage.
Yeah. Does it make sense to you now?
Yeah.
Yeah. So because of that, we have one chance to override the whole thing. And this is how we're going to override it. We have 14 bytes of garbage to fill the buffer. And we have 4 bytes of garbage to fill the val-fools saved EBP. Then we have 4 bytes of return secret address. Another 4 bytes will actually be the saved EBP for print secrets, and the value doesn't matter. Okay. And higher than that, we should have 4 bytes of the parameter. Okay. So the key here is this 4 bytes. You need this 4 bytes to do that. Any questions? Okay, so let's try this. Let's try this. Return 2. We are doing how many bytes? We're doing, this is 18 bytes. Then the address of a print secret, which is 38, 63. Okay. So if we only put those addresses there, what will happen? We're going to return to here. However, I very unlikely to be the value we set there, right? So we're going to get IPT to C. Are we getting segment fault? We're not getting segment fault because there is excess there. So if we do this, we do get a segment fault. How did we get a segment fault? Where are we? Oh, it's possible that I'm using a 2 different version of code here. Let me see. Let me go down for this. Okay. The reason we're getting a segment fault is the code I'm showing on my slides and on our server they're not exactly the same. This version doesn't make that system call to exit. Okay. This one actually returns. So I add that exit later, and we didn't push the latest version of the code. That's why. But that's not the point there anyway. Okay, cool. So when we get here, we are going to get IPT the pool. So if we want to get, so what should I do here? 4 bytes of garbage, right? 4 bytes of garbage, then another 4 bytes of that 1, 2, 3, 4, 5 thing. So which line is lower? 28, 56, 34. So this should work. Right? So this gives us the plan. Okay, if we change the value a little bit from 12 to 22, it should give us IP to the full, right? Make sense?
Like, just a thought I had, but this is possible only because the stack goes up that height. It's possible that the stack does not have enough depth for us to go up.
So what you are saying is we cannot override so many bytes. Is that your question? Yeah, that's very possible. Yeah.
Let's say the print secret had like 20 arguments,
Yes.
then you cannot override the number of.
Actually, even if it has 20 arguments, you can override. As long as you are only returning to that function.
But the stack goes downward. So
No, here, you're not pushing things to the stack. You are creating fake data on the stack. And the way you are creating fake data is from lower address to higher address. Not the same direction as how the stack works.
So, but basically there is a like limit stack. You can't override more than.
Yes, but usually that's
Maybe-
several megabytes. So that's not a problem. Yeah. But we're going to talk about something there is you can see that by doing this, we can chain functions together because their return address are not overlapping. They're always 4 bytes higher. So as long as those functions, they do not have parameters, technically you can chain as many as possible, right? Even if they have parameters, there are ways to chain it. And that will use return-oriented programming, which we're talking in the second half. But I will show you how we can chain those functions together next. So will our class be over for 4:30? We have 30 minutes. Cool. Okay, so we already tried this. We can return to directly print flag. But that's not what I want you guys to do. Okay, so we can also return to functions with multiple arguments. Right? That's what you said there. This is a slightly different program. The only difference is the print secret takes 2 arguments instead of 1. Right? So this is actually quite simple. As long as you understand this one. We go to return 3. I assume the buffer size is the same. So it will be 18. Then we'll further. 18. It's about address. So 18, after 18, we should put the address there. Which is 58, 63, 55, 56. After that, we need another 4 bytes of garbage. After that, we should put the value. The first one was 78, 56, 34, 12. Then the next 4 bytes will be deadbeat. It will be there. There, over, there. B80, right? There, there, B. Okay, this should have that. Okay, great. So with 2 parameters, we can also get this. Of course, I mean, any of this, you get 1 off, 1 byte off, you're not going to get the flag. Right? Anywhere you make a tiny mistake, 1 byte, or even let's say I'm actually changing half byte, right? You're not going to get it back. Okay, so this one makes sense. Okay, now can we return to multiple functions? So we were able to return to one function, no matter how many parameters that function has. Now let's say if we can return to multiple functions. We actually can. Okay. So let's say this is the stack of Volfu. EBP points to save the EBP. So put garbage there, I just quit it. Okay. The return address will be at F1. Okay. We put a function one's address there. Then we can put argument one's address there, argument two's address there, right? No, argument two of no, argument one and argument two for the function one, their value, not their address. So then after Volfu returns, the EBP will have the value A, and the ESP will move up to this place. So then to that F1, for that F1 will think these 4 bytes is the return address it's going to use. And the beauty is this 4 bytes doesn't overlap with the previous Volfu's return address, which means technically you can chain them together, right? Let's say technically we can chain them together. We put F1's address here, 4 bytes higher, we put F2's address, 4 bytes higher, we put F3's address. So Volfu will return to F1. F1 will return to F2, F2 will return to F3. So we can chain many functions together. However, the problem is those functions, you cannot have arguments. Because the argument's address, let's say F1's argument one's address overlap with the return address for function 2. Okay. Unless they are the same number, I mean, very unlikely, they overlap. Yeah.
Why are they not pushing the EBP? Because the first one is to push the EBP. Right?
They are pushing.
So where will that EBP of everyone?
That's a good point. They actually were overflow this one. They were override it, but doesn't matter anymore. As long as you're in F2, this value doesn't matter anymore. They were pushed here. So F3, when you are executing F3, it will override this, but doesn't matter anymore. Yes, exactly. Okay, so now let's play a little game here. We have 5 functions, F1, F2, 3, 4, 5. Each function print out 1 word. Knowledge is power, grass, bacon. Okay, so that's, and we're going to print out. So how many of you know knowledge is power, France is bacon? France is bacon. You guys know that? It's a joke. I mean, there's a website about that. There's a website about that. It's a funny story. That'll be part of your homework. So we have the Volfu here, 6 bytes, the same, and we print out the address for all the functions. Yeah. The goal here is we're going to chain those functions together. Print out the so to print this out, obviously we first return to F1, the F2, F3, F4. Then we need another is, right? France is bacon. So we're going to return to F2 again, then F5. And we just need to put their addresses together, one by one, right? So let's do this. The overflow return chain setting. When we run this program, print out the address for us. Oh, how many bytes? How many bytes of garbage we need? Maybe the same. Yep, the same. It's here E 14. So we need 18 bytes of garbage. So we need the 18 bytes of garbage. After that, we have the first address. First address will be 2D 62 55 56. So by doing this, we're not doing anything different from what we did before. We're returning back to only one function. Right? So this should print knowledge for us. Why it's not printing out knowledge? But oh, I mean 2D, right? 2D still not correct. I think it this we're not showing anything. It's because the program crashed before the OS had a chance to print it out. Yeah, that's why actually at the very last one I have a exit 0. This one have an exit 0. So if we put exit 0 there, let's show it. So the last function will be A1 62 55 56. Okay. So this should print out knowledge bacon. We actually print out knowledge bacon for us, right? So we are actually returning to two functions, chain them together. The difference between this one and this one is because how always handle this is when you do a print or put, you will put it into some system buffer. It do not directly go to the terminal right away. It may buffer something and later put everything to the terminal. So before the OS had a chance to print that out, this program already crashed. That's why we didn't say that. But here we call exit 0. Okay, so it makes a system call to gracefully exit. That's why we do not say second and fourth, and we say the whole string there. Okay, so if we add everything together, what is the second one? Will be 4A 6 2 5 5 5 6. So we add six 7 6 2 5 5 5 6. Now we should have knowledge is power then bacon, right? So that's what we have now. Then we add another 2, then we're done. Press should be 34 6 2 5 5 5 6. Now we are going to add another return to the function prints out is, and that one we actually call twice, return twice, which is 4A 6 2 5 5 5 6. Okay. that should be it. So that is how we print out knowledge power transistor, right? So this one, we call this function twice, means it's return into it twice. So in the homework, you are going to do 32-bit and also 64-bit. They're actually the same, right? You just need to figure out the address and type more bytes in, and you need to figure out how many bytes of filling you need there. So what?
Okay, that's right. On my end, invited with knowledge is power, knowledge is bacon.
Okay. Yeah.
Perfect.
Okay. There's one reason because at the end of bacon there is an extra zero, right? So bacon has to be the last one.
Mhm.
So after you print out bacon, you will not print anything else, basically.
Oh, yeah, this
Yeah.
was, I was trying to do knowledge is power, France and bacon,
Okay.
but
Yeah.
did knowledge twice.
Okay. Cool. Okay. So I guess we will stop here today. And we still have like 40, oh, maybe 20 minutes. Then we can work on the homework too. Show me what you have done so I can answer some questions. So next week, we are going to do our very first share code, which you already saw a piece of that. And then we're going to dissect the very piece you saw probably, I think it's sort of almost a full share code. Yeah, but we're going to dissect it again, understand that. Then we will have several tricks to inject the share code into the address space. Then we can execute arbitrary code. So the share code we're going to say next week is a simple one, but you can develop very complicated share code to do whatever you want to do. Okay, so we have 20 minutes. I will walk around and just show me your homework too. Great. You said you have some questions, right?
So, oddly, in the.
Right.
So I think. I'm trying to. Figure out the result of it. So I think reference about the same. You're good.
Okay.
So I. So 0, 0, or 0, 2 is the lowest. 2. 0.
Oh, so okay. The number you have is. Do you want to do number of 2 or?
So at the end of the day, I think that these are the text values that I need to be.
Okay.
But before I
Yes.
even get to that, I want to make sure that
Okay.
I understand how to load
Okay.
any number.
But the number you are showing me, how big are they? 4 bytes or 2 bytes? Yes, 4 bytes. Not 2 bytes.
So
For example, you put another 0. No.
okay, so then I just do that one more.
Yes. Yep. Work.
So
So capital again, start from beginning, I guess.
these are written all at one. So Oh,
Okay, that's the problem.
okay, so I was overriding
Yeah,
4 bytes when I thought I was overriding 8 bytes.
yeah, you're overriding 4 bytes, so you're basically multiply a random number because the second four,
Yeah.
you didn't do anything, right? It's a random number.
Oh,
Then I don't know what is that. 20020, what value that is. Well, you're getting a random number to
Yep.
multiply that number. That's
Yep.
why the number you do not recognize. Yeah.
Yep.
Okay. Right. Homework is done. Okay. Well. Okay. Cool. Yeah. You try Overflow 5. You did. Yeah. Yeah. We're still having a class.
Oh, so,
Yeah.
sorry.
Yeah. So, remember what that means. I didn't think about. Yeah. 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 It's good. Good. So what kind of debugger do you think about debug? What kind of game? Windows game or? Yeah. Okay. All right. What are you working on? Okay. Why you guys? Okay. Which one is this? Okay. You're missing X there, the syntax. So you see the 55 and 56. Yeah, so if you miss the X, you're not giving the hex in that. So one way to do that, and one way to verify this is you need to verify your input. And after that, there's a slash. The slash, you have the F, you're using a forward slash to be backwards. Now, yes. Still some errors there. With the address there. Okay, this 4 bytes. You don't need that copy 4 bytes. Now that together, you don't need that. You don't need that. Yeah. But you need to understand why you don't need that. You need the whole thing. You don't need that. You don't need that A either. So, okay, let me see. That's 4 bytes. You do need that one. Oh, you have. Okay, can I try? There's a syntax error. I cannot tell. Looks like a quote or something. Yeah. One of the quote. Oh, yeah, you need to close there. No, you cannot have a space there because the space will be a value, right? And you cannot have that space. Okay. Yes. That's how we do. And that's how we can say it. Yeah. Yeah. Okay. Back to getting there. Okay. Bottom two. And the bottom parameter. Yeah. What you do? Right. This is the, yeah, look for the function you want to analyze, like more. don't need to do that. And even about which line? Low cost point. Okay, maybe just it doesn't even allow you to do it, right? But they just focus on line. That'll be easier. You don't need to understand it. So the key here is which one calls get and this is get. Then I only do the think of the this is get. The gets have only one input, which is the average of the. So how does the parameter get passed? Pass that by proofs, right? So before the call is instant, which means EAX has an average. Then go check what is the EAX of it, go backward. Okay. The EAX has a value of so. No, no. This, the same the EVP is provides, the current address is provided. But that's for 32 billion. It's a 4 billion already. All right. Okay, this one. Yeah. So this one, the first attacker is where the buffer. So the buffer is at EVP minus 12. 12 is what? It's 18. Then what you're trying to override is this variable. And that variable is at EVP minus 3. So what's a distance between 3 and 12? That's 6 bytes. Right? 3 is 12. Yeah. Which means buffer here is actually 6 bytes. So buffer, you don't care what you put in buffer. You need 6 bytes of garbage. Okay? So every byte after that, will the 4 bytes after that will go in. It's garbage. You don't know what is there. Yeah, you don't know what is there. This is stack. Nowhere actually cleans that. So you literally do not know what is there. And you are going to override something, but you also do not care what it is. What you care is overrun here. Yeah. Find out where the buffer, because the reason you want to find out where the buffer is because you are overwriting starting from buffer. That's the address you start overwriting, right? Then find out what is the variable you are trying to override, what is the distance with the buffer. Then you know how many bytes you should override. And also figure out what's standard you need. Mhm. That's the overriding the return address. Not overriding the local variable. So this one is overriding local variable. Right? Yes, because this is a sequential override, you do override everything you're doing, but you don't care about the letter. It does not matter. What you are really trying to override is which is happening. But the vulnerability only allows you to do a sequential override. That's why we have all of garbage in the middle, fitting in the middle. Doesn't matter, don't matter. There may be other vulnerabilities that give you an arbitrary override. So you will not do a sequential override. The override will return. So when you override the return address on the stack, so when the function you are executing right now when it returns, you will not return to the original place you get called. Instead, it will return to it anyway. That's not a return instruction, that's a return address. Other functions has return instruction or even multiple return. That is possible. Um, and when return instruction is executed, we look for what address return should return to on the stack. And you overwrite that address. Change that address. That address was there originally by the core function, the core instruction, to the address. And now you change that address. So you will not go back to the core site. You will go to any other place you wanted to go. Free pointing? What do you mean by free? It's a code pointer, obviously. It's pointing to wherever you want it to point. So I'm going to start with put that to print flat. Yeah, or print secret. The next task we're going to change to other things. Yes, yes, exactly. Okay. Okay. Yeah. Yeah. Yes. Which one do you give the one? Yeah. No, I'm not sure about that. I do not really know what that S should be string. I'm not sure what does it mean there. Maybe the B doesn't mean anything with string. Well, but maybe that together it doesn't mean anything. Yeah, yeah. So maybe well to me it looks like it was yeah 1 byte is basically 1 byte. So in this case, the string is uh, I guess the B doesn't matter. I mean, if it's a string, why does it matter if it's B or B or H, whatever? It's a string. So that's we're treating it as Unicode. Yeah, this is obviously Unicode. Yeah, so we're treating it as Unicode. Yeah, of course. Yeah, of course. Yeah, because that's how strings defined. And with a zero. Movie what? Yes. Yeah, move your there is a bracket. Yeah. Yes. Yeah. What is the higher one? I mean, we're using that instruction to move to a register, and a register is 4 bytes. Data is also 4 bytes. You do memory to memory? Yes. Yeah. Go higher. Yeah. Yeah. Yes. Yes. Because whatever we give, it will be copied to the memory, right? The bytes we give first will go to lower memory. Because when we do a copy, we copy from lower place, lower address to higher address. Yes, exactly. Right. So that's why Want to put a higher height. You do higher end of it, it will get them later. The lower line. Yeah. Okay, cool. So that's great. From there, you do everything. As we do the it's always like you might that's where the other. The where the data is, and you are really to. And the you're trying to memorize things you're still trying to memorize. Why is that in the United States? Why is that in the United States? So those are the two areas that in the area. No, I mean, what's you still thinking you might have killed it and you didn't might have over that. I think heads, that's a key. Yeah. You're here to say you're being. Starting to minor mistakes. Well, what we do. Basically, you were and this one, yes, let's look at the values, right? Okay. This value of time is value, you should be for this. And then I have a point. I put prime there, so. The online tool, but I didn't got the video. That's actually originally midterm CPF. Obviously, I wanted to write a code to factor the prime. So I give a hint there. I mean, there's two of them. Okay, I guess that's it. I will see you guys. See you guys next Tuesday, and I will be outside if you have more questions. Yeah.
Enjoy your weekend.
So you don't have more questions anymore?
I got it. Yeah, I did.
Good.
My biggest issue was not understanding how big a bite was,
Yes.
and I think just not realizing it was in Max.